Hi everybody. Today we'll be discussing limits involving trigonometry and trigonometrical functions. So let us just have a little brief overview. So sine x and cosine x, these are two of the most famous trigonometrical functions. These are continuous for all x. Okay, and then let's look at secant and tangent. Secant and tangent both have the same discontinuities, and these are discontinuous at all x which are equal to the quantity 2k plus 1 times pi all over 2, for k being any like integer. It can be plus or minus. So it can be 0, -1, +1. So that's what the plus minus sign comes for. And then cotangent and cosecant are together. So cotangent and cosecant x, they are discontinuous for x being k pi, for any multiple of pi. So positive pi, -17 pi, all of those. So it's for the same k being a positive or negative integer. Okay, so now that we have this done, so let's go for our limits computation. Okay, so from the trig identities video, we can recall three of the most famous Pythagorean identities. The first one being sine squared theta plus cosine squared theta is equal to 1. And this comes from the triangle, the right triangle, which has theta as the angle, and then 1 as its hypotenuse. And then we have that if this are true, this must be sine of x, sine of theta, I mean, and this must be cosine of theta. And when we divide all of these terms by sine theta, then, well, we get the following, which is 1 plus cotangent squared theta is equal to cosecant squared theta. And if we were to divide it by cosine squared theta, we would get the following. 1 plus secant squared theta is equal to tangent squared theta, or that tangent squared theta minus 1 is equal to secant squared theta. So these are the three Pythagorean identities which we can plug in if we see any of these types of expressions. So let's get into limit computations. So let's look at the first problem. We have the limit as x approaches pi of the quantity the square root of 3x squared minus 1 all over sine squared x minus cosine of 2x. Now you might see here, oh, why should we wait for getting to our 0 over 0? We should just calculate some things and simplify. But wait, let's first do it. Let's first plug in our values. So as we remember, we have our first strategy for limits is direct substitution. Then if that doesn't work, then we go to algebraic manipulation. And in that, we can factor terms, we can factor quantities, we can rationalize, and if none of those work, we can try trigonometrical factoring or whatever. So let's first do some direct substitution. So we have the square root of 3 pi squared over minus 1 all over what is sine of pi. As you might remember, sine of pi is just equal to 0 because it's on the x-axis of the unit circle, and the y value for the x-axis is just 0. So 0 squared is equal to 0. And what is cosine of 2 pi? Well, cosine of 2 pi is just the same as cosine of 0, which is equal to 1. So we just have that this limit is equal to the negative square root of 3 pi squared minus 1. And that's our answer. Let's look at a few probably harder questions. Our next question is that what is the limit as x approaches 0 of sine cubed x over sine x minus tangent x? Well, this might seem pretty hard, but let's first do our direct substitution, as always. Well, the top is 0, and then on the bottom we have 0, and sine over cosine is equal to tangent. Well, the sine here is equal to 0, and the cosine is equal to 1, so it's just equal to 0. So we just have a regular 0 over 0 indeterminate form. How are we going to now simplify things here? First, let me clear this up. Okay, so remember that we have that tangent x is equal to sine over cosine. So let's plug that in. So we have our term here, and I'll just rewrite it like this. So we have this term sine x minus sine x over cosine x here. Okay, now we can factor a sine x from the top and the bottom. So we have the term on the numerator, we have sine x times sine squared x all over sine x here, and then we have 1 minus 1 over cosine x. And now we can just cancel these out, and let me write on the here what we have remaining. Well, we have sine squared x over 1 minus 1 over cosine x. Now, what are we going to do? Well, we can just try to figure a way we can put this into one whole fraction. So let's just do this using the butterfly method, which you might have heard of. So in the butterfly method, you just multiply the denominators, and then you multiply this and this. You do cross multiplication, and this means that this would just be cosine x minus 1 all over cosine x. And because we're dividing, we're just going to multiply this sine squared x by the reciprocal, which means that this is equal to sine squared x times cosine x over cosine x minus 1. Now we can just combine this, and we can see that sine squared x is just equal to, by the Pythagorean identity, it's equal to 1 minus cosine squared x. And this is equal to the negative value of 1 minus cosine x, which is a factor of this. If we were to cancel out these terms, we would just get 1 plus cosine x here times cosine x multiplied by a negative 1. So this whole thing would just be simplified to the following. Negative cosine x times 1 plus cosine x, all stemming from the Pythagorean identity. And this one term must be much simpler to take the limit as it approaches 0. So let us just directly substitute this in and see if we have it completed. So the limit as x approaches 0 of negative cosine x multiplied by the quantity 1 plus cosine x is equal to negative 1 times 1 plus 1, which is 2, which equals negative 2. And so we have our limit completed. So this is how we can compute trigonometrical limits pretty simply. And now we're going to discuss a different limit. What is the limit as x approaches 0 of sine x over x. Well, this one we're going to be covering in the next video about the squeeze theorem, but if you want to try computing this with trigonometry, you can try doing it and you can put your answer and your deduction of your method of how you solved it in the comment section below. So thank you all for watching. I hope you guys enjoyed this video and were able to understand how to compute limits by plugging in trigonometrical identities and using trig functions. And in the next video, we'll be covering the squeeze theorem, which will be helpful to solve this other very fundamental trigonometry limit, which will help us do many other types of trig limits. So thank you all for watching and have a nice day.